Oh, first of all, the second exam will be on Friday, March 9th, and the final exam during the semester will be on Friday, April 13th, if you want to put those on your calendar. So today I'll continue to discuss about bipolar device modeling. Hopefully we'll have a reasonable understanding of how that transistor operates at the end of this lecture. We saw that there were two ways to make a bipolar transistor. One with stacking an NPN region together and one stacking a PNP region together. So in that sense, they're symmetric. But in contrast to the MOS device, they have some lack of symmetry. And what is that lack of symmetry?
Electrical symmetry.
The electrical symmetry is different because the doping levels of one side and the other side are different. So we agreed by convention to dope one side heavily. We'll call that the emitter, and the other side is lightly doped. We're going to call that the collector. And what characteristics did we say were important to get a good beta on the transistor? What characteristics on these junctions? The thickness of the base, right? If the thickness of the base is very, very, very thick, the minority carriers that get in that region will exit as base current. But if that region is very thin, a high percentage of those minority carriers will contribute to collector current. What parameter characterizes the efficiency of those minority carriers in the base region contributing to collector current? Alpha. And what's alpha typically between? It's between 0 and 1. For a good transistor, it's very close to 1. But we don't use the parameter alpha very often to characterize the bipolar transistor. We choose to use the parameter, what do we use instead? Beta. And beta and alpha have a one-to-one relationship, it's a bilinear relationship. And we'll find that it's difficult to accurately measure alpha, but we can accurately measure beta and calculate alpha if we want. Yes, you had a question? Yes? No, okay. We talk about how the device is operated. Then we look at the forward active region. And when we describe the operation we described was in the forward active region. And we said that the bipolar transistor really behaves as a current amplifier. In contrast, how does the MOS transistor really behave? As a transconductance amplifier. Controlling voltage determines the drain current in a MOS transistor. But controlling current controls the corresponding current in the collector in a bipolar transistor. We also observed that the relationship between the base current and the base emitter voltage was governed by the diode equation. So there's an exponential relationship between those parameters. And then we saw that the collector current was proportional to the base current. The proportionality factor was beta. And then we wrote down an analytical expression for the model of the transistor, but we changed parameters. I introduced the operation with the parameter IS tilde, but we said the industry probably prefers to put the beta term in the base current expression rather than the collector current expression. So we have the model that we have in the upper right in the forward active region. So here's the model that we've got so far. And then we said that if you get to lower reverse bias, put less force on those minority carriers when they enter the base region, the efficiency goes down, and the collector current drops down. And those are the regions of operation that we identified for the structure. Actually, if you look at a voltage axis comparable to what we might use for a MOS transistor, we see that there's really a very abrupt drop off on the characteristics when the reverse bias on the base collector junction gets smaller. Goes down much more quickly than it does in the MOS case. So here's kind of a comparison of the MOS transistor and the bipolar transistor, maybe under comparable VDS or VCE values. Now, if you look at the device operating in the forward active region, we actually see a little bit of slope here. And we saw that slope in the MOS transistor as well. Well, the bipolar transistor was around first, and there was a guy named Mr. Early that discovered the effect of that slope. And he observed that effect in the bipolar transistor, not the MOS transistor. And he observed that if you project back a tangent line back to the second quadrant, you observe that all of these intercept the negative VCE axis at the same point. And hence that voltage became known as the early voltage. Okay. So the early voltage is the interception. If you go way back here, and a typical value of the early voltage is maybe 150 or 200 volts negative. Okay. Now, when we accounted for that slope in the MOS device, we simply modified the drain current expression by 1 plus something times VCE. And that something was reciprocal of that voltage where the intercept was at. We do the same thing in the bipolar case. We can multiply it by the expression for IC by the term 1 plus VCE over some constant quantity. That quantity, as we said, was the early voltage. So we're going to multiply the collector current by 1 plus VC or VF, and that'll be an improved model of the bipolar transistor. We'll do that in just a minute. So here we have the approved model in the saturation, in the forward active region. We just multiply this by 1 plus VC or VAS. Don't need to do that in the base current expression because there's really no justification for doing that there. So here is a better representation then of the output characteristics of the bipolar transistor. A little bit of slope. I've exaggerated the slope here on these curves. Same regions we've identified before. This is a model of the bipolar transistor that's valid in all regions. It's valid in the forward active region, it's valid in the saturation region, and it's even valid if you let VCE become negative and VBE become negative. It's also valid in the third quadrant here. This equation is called the Ebers-Moll equation. And if you look at that equation, we have a collector current that's the sum of two exponential terms with different coefficients. And when it's expressed in this form, they chose to use the emitter current and the collector current as the dependent variables. We choose to use the base current and the collector current usually as the dependent variables. It makes no difference. Any two of the three is sufficient, right? But there's a problem with this equation. If you want to analyze even a single transistor circuit, one transistor, one resistor, the analysis with this equation is completely untractable. Remember, we tried to solve a simple resistor diode circuit, one resistor, one diode, and we had a difficult time getting, well, we didn't get a closed form explicit expression. This is worse because there's two exponentials here. So we can put something like this in the computer and use this as a computer model, but analytically, this is not very tractable. But this is valid in all regions of operation. We can add the VF effects. They're not even in here yet. So if we put early voltage effects in, it gets even more complicated. Not easy to work with. We call this the Ebers-Moll model. Now, if you're in the forward active region, we're going to see that VBC is reverse biased. That was our assumption. VBC is typically much less than the thermal voltage. So this is 1 over e to some large power. So this is orders of magnitude less than 1. So in the forward active region, this term is negligible. And this term is of the order of magnitude of a femtoamp. So we can neglect this term here, and it reduces to essentially the diode equation in the forward active region for both the emitter current and the collector current, and correspondingly and for the emitter current and the base current. If I look at the relation between the collector current and the collector emitter voltage under both positive and negative values of VBE, we find that when we get to the third quadrant, we get a big compression of the curves. This region of operation here is called the reverse active region. And it's analogous to letting the emitter and the collector play different roles. It's analogous to letting the lightly doped region become the emitter. So we forward bias then the quote base emitter junction here, and then we reverse bias the base collector junction. Now, what happens is, since these curves are much closer spaced, the corresponding beta of the transistor goes way down. So most of the time when we want to use this device as an amplifier, we operate in the first quadrant. But if we were to change the role of the emitter and the collector, we could still make it work like a transistor, but maybe with very horrible properties. So, since we don't have a good model that's analytically tractable in the saturation in the saturation region for this device, let's see if we can get an approximation that's reasonably good. So, since these characteristics drop very rapidly here, I'm going to just assume that we can put a vertical line in here and assume that when we enter saturation, the collector emitter voltage is constant. If I do that, and those all go down at about 200 millivolts. If I do that, a simplified model in the saturation, this is a simplification of the Ebers-Moll model, will be VBE of about 0.7 volts. Remember, we forward bias the base emitter junction. And then the collector junction, VCE is going to be 0.2 volts. Not too bad of a model. Okay, so that's an approximation of what goes on in the saturation region for the bipolar transistor. So now I can give a piecewise model for the MOS transistor like we did for the bipolar transistor, like we did for the MOS transistor. We have the exponential relationship in the forward active region we developed before. In saturation, we have VBE of 0.7 and VCE of 0.2. And in cutoff, the collector current and the base current are both 0. Okay. Why do we like piecewise models?
They're all easier to calculate.
It's a lot easier to calculate. If you can guess which region you're operating in, then you got a simple model to work with, and all you have to do is verify the region of operation. So we need to get the boundaries for these regions of operation. Now, this is not quite as elegant as I would like it to be. This model is pretty good as long as the base emitter voltage is above about 400 millivolts, a reasonable forward bias on the junction, and as long as the base collector junction is reverse biased, VBC is less than 0. The saturation region expression is usually pretty good as long as the collector current is less than beta times the base current. And the collector current and the base current are approximately 0 when both junctions are reverse biased. What I don't like about this is that the conditions are now dependent upon dependent variables here. if you look at the MOS device, our conditions for operation were always dependent upon the independent variables, the gate to source and the drain to source voltages. In this case, the expression for the saturation region, the conditions are dependent on dependent variables. But it'll still work with us. It'll still work. Here's an alternate equivalent model. Notice that the collector current is about beta times the base current. So we can say the collector current, instead of having the exponential term in here, we can just say it's beta times the base current times 1 plus VC over VAF. So either expression should be adequate. They're the same. I'm going to do a little bit of a further simplification right now on the model of the bipolar transistor. In the forward active region, the base emitter junction looks pretty much like a diode, and the collector current is about beta times the base current. So in many applications, we can simply model the base emitter junction as a voltage source of 0.6 volts and the collector current as a current dependent current source of value beta IB. And this model is pretty much valid provided that in your circuit it doesn't make much difference whether the base emitter voltage is 0.6 volts or 0.7 volts. And we'll see in a lot of circuits, it doesn't make much difference whether the base emitter voltage is 0.6 volts or 0.7 volts. So this is a simplified, this is a further simplified model then. Collector current is beta times base current, and neglect the early voltage if you use the simplified model. The base emitter voltage is about 0.6 volts. The conditions for being in the forward active region don't change. They're the same as they were before. So now I'm plotting the regions of operation of the transistor in the VBE VBC plane. Those were the independent variables. And we saw that when both junctions were reverse biased, that is, when the VBE is negative and VBC is negative, it's in cutoff. We've got an expression for that. And then we said when VBE was above 0.4 volts and the base collector junction was reverse biased, we're in the forward active region. I didn't give the conditions, but if the base collector junction is forward biased and the base emitter junction reverse biased, we're in the reverse active region. And if both junctions are forward biased, we're in saturation. Both junctions are forward biased by more than about 400 millivolts. I got a little problem here. Because the models I have apply to the regions I've defined. And there are some places here we don't have a model for. Is that disturbing? If you look at the MOS transistor, you can take any value for VGS, any value for VDS, we had a model. Now, we've got a model in the forward active region. We've got a model in cutoff. We can easily get a model in reverse active. We can get a model in saturation. But I've got this region in here where I don't have a model. Well, I do have a model. I've got the Hebert-Boole equations. So do we have to worry about what goes on in between here? No, why not? Your answer is correct. We usually don't have to worry about it. Why don't we have to worry about it? Any idea? Yes?
You just design the circuit so that it operates higher than that 400 millivolts.
Great. Good solution. We'll just agree beforehand that we won't design the circuit to operate in those regions. Then we don't have to worry about modeling it there. That's a good practical solution, isn't it? What if there were some good circuits that we're missing out on in that region? So you got a good suggestion. We just avoided the modeling problem by agreeing not to work in that region. But what if there were some good circuits in that region? Would that be disturbing then, if we agreed to not use operation in that region? Probably the answer is yes. I'm not aware of hardly any circuits that are useful that are designed to operate in the regions that we've not identified here. Okay, so we won't be so concerned about not having a model in these regions that are not defined here, because we probably won't use it there, and there's probably not very many good circuits that are useful there. Can we get some intuition why there might not be good circuits that are useful in this region? Can we get some intuition why that might be the case? Well, in this region, the device behaves as the Ebers-Moll equation, and you can't neglect terms of that Ebers-Moll equation. If you neglect some terms of that Ebers-Moll equation, you move up into here, or down to here, or over to here. Usually, if you have an extremely complicated system, it's hard to design useful circuits that have those really complicated devices. Does that make sense? Okay, so we're not going to worry too much about it. Now, there's a portion of this region here that we've identified that we're not really interested in. If you look at that exponential relationship, the e to the VBE over VT, or e to the VC over VT, when you forward bias those junctions, what happens to the currents when the base emitter voltage gets much above about 700 millivolts? What happens to the currents when the voltage gets above about 700 millivolts? Mr. Strong.
They flatten out. They pretty much stay constant.
No. If that was the case, it'd be good. The current is equal to something e to the VBE or VT. What happens when the base emitter voltage gets much above 700 millivolts?
It will just exceed the rating of the transistor.
Yeah. You get amps or tens of amps or hundreds of amps or kiloamps of current flowing. So you get monstrous currents and big voltages, and you get watts or tens of watts or hundreds of watts or kilowatts or tens of kilowatts of power dissipation. And immediately the device will destroy itself. Okay? So when does that happen? When both junctions are forward biased. So you get very, very far up in here. Don't have to worry about modeling it because the device will destroy itself. Here, base current gets too big, it'll destroy itself. Here, over about 0.7 volts, the device will destroy itself. So we don't care about modeling it in these regions here, unless you enjoy watching it destroy itself. So we have a meltdown region right here. So really, all we're concerned about is modeling it in the cutoff region. This little band here is forward active region. A little bit in the saturation region where we don't destroy it. And in a few cases, not a big instance in this course, in reverse active region where the collector and the emitter flip rolls. Okay. The reason I'm not very interested in this region is, again, there's not very many useful circuits that operate in this region here. So how did we model it in the saturation region? Do you recall what we did? Well, we just assumed that the base emitter voltage is about 0.7 volts, and the collector emitter voltage was about 2.2 volts. So we just modeled it, and if the collector emitter voltage is 2.2 volts, the base collector voltage is about 0.4 volts. So we just model it as a point in this region here. That's that red dot. The other red dot is where we would model it in saturation if you were in the reverse mode instead of the forward mode. Now, the models that we have can actually be extended to narrow this region down quite a bit. For convenience, I assume that when the base emitter voltage was less than 0 isn't cut off. But if you look at that exponential relationship, e to the VB over VT, as long as the base collector voltage is below about 0.4 volts, there's hardly any base current flowing. So I could really extend the cutoff region up to about 400 millivolts. So there's just really a small band in here where I don't have a model for. Does that make sense? So here's the regions that we're concerned about right here. Let's look at an example. Let's determine IC and V out for the circuit. How do we proceed? Well, we have a nonlinear device, right? And we have a piecewise model, right? So what do we do when we have piecewise models for nonlinear devices?
Make a guess.
What?
We make a guess.
We make a guess for the region, analyze the circuit, and verify. Okay. At this point in time, unless you've already worked with bipolar devices, you may not have an intuition as to what region to guess. You'll get that intuition very quickly. If we guess wrong, are we going to make a mistake? If we guess wrong, are we going to get an incorrect answer, I should say, if we guess wrong?
Your answer won't verify.
It won't verify. So we won't get an incorrect answer. If we guess wrong, it will not verify, then we have to guess a different region. Okay. So let's guess the region we started with. Let's guess forward active. And I'm going to try to get by with the simplest model that I can get by with in the forward active region. So in the forward active region, we said the simplest model we have was a 0.6 voltage source and a collector current that was equal to beta times the base current. So let's guess forward active and use a simplified model. If I do that, I'm going to draw the circuit, and then I'm going to wave my hands at it on the screen and try to do the same thing. So I have 0.6 volts here. I have beta IB, and the collector is tied to a 4K resistor up to a 12 volt voltage source. And the base is tied to that same 12 volt voltage source through a resistor of value 500K. And in order to verify, let's write down the verification conditions before we go on. What were the verification conditions for operating in the forward active region?
Sorry, I haven't been paying much attention.
Mr. Day.
VB needs to be positive.
VBE is bigger than 0.
And VC is less than 0.
VBC was less than 0. Base collector voltage was negative, and the base emitter voltage was bigger than 0, or I think we said bigger than 0.4 volts. Okay, so these are the verification conditions. So now let's analyze the circuit. What's the base current? IB is equal to 12 minus 0.6, 11.4 over 500K. Okay. The collector current, and I assume that beta is 100 here. The collector current is beta IB, so it's 100 times this. So it's 11.4 over 5. Okay. If that's the collector current, the output voltage, V out, will be 12 minus the collector current times 4K. So it's 12 minus 11.4 over 5K times 4K. The K's cancel, so it's 12 minus 11.4 over 5, which is 12 minus 2.
You still need the 4, right?
Oh, yeah, you're right. Thank you. Twelve minus 0.8 times 11.4. And what does that come out to be?
So 0.88.
2.88.
Yeah.
So 12 minus 2.88 is 9.
No, the whole thing is 2.88.
Pardon? Well, this whole thing is 2.88.
88.
Okay. So that's the output voltage of the circuit. Now we've got to verify. Is VBE bigger than 0.4 volts? Yeah, it's 0.6. Is VBC less than 0? So VBC is equal to 0.6 minus 2.88. Okay. And that's less than 0. So we verify the region of operation, and our output voltage is 2.88 volts. We might want to check that we can get by with a simplified model. How can we verify that the simplified model was adequate? We said put 0.7 volts in, solve it again, and if there's not much difference, we put 0.6 or 0.7 in, then this is pretty justifiable. So if I put 0.7 volts here, this becomes 11.3 over 500K. This is 11.3 over 5K. This number here is, instead of 11.4, it's 11.3. This will be just slightly bigger than 2.88. So we don't see much difference in the two outputs. So our simplified model is valid as well. Make sense? Okay. Oh, I forgot to use something. What did I forget to use here? What?
J and A.
I didn't use these terms here. Why didn't I use them? Didn't need to. You have all the information about something, and you may have information that's not relevant. So it tells you this circuit is not particularly sensitive to some of the model parameters. The model parameters in this are what? JS and beta, right? Those are the model parameters. Since we didn't have to use JS here, that means this circuit is not sensitive to JS. As a designer, it's not as sensitive to the emitter area. That's kind of a bummer. Circuit designers are control freaks. They want to control everything. In this case, the emitter area doesn't do anything for them. Well, that's not too bad. It's all right to have something that is pretty much close. How about beta? Is this circuit very sensitive to beta? Yeah. If we change beta, we change this current a lot. And if we change this current a lot, we change the collector current a lot, we change the output voltage a lot. So we can conclude that this circuit, the designer has no control over the characteristics with the emitter area. The parameter JS doesn't affect things hard at all, but it's highly sensitive to the parameter beta. Is that a good property? Highly sensitive to beta? Yeah, usually not. Usually not. Reason it's usually not the case is if you take different transistors in a process, there's typically a fairly big variation from beta of one device to another device. Even worse, if you have devices from different manufacturing lots, the betas will vary a lot. So you might have a nominal value beta of 100, but from one process lot to another, it might go between 80 and 150. Does that make sense? So if you designed this circuit, fabricated in a process, and sometimes it came out at 100, and sometimes at 150, and sometimes at 80, the circuit would be all over the place. So the same circuit. In this case, I'm only changing one thing, and that's the base resistor. Okay? Since we were successful last time by guessing the forward active region, analyzing the circuit, I'll do the same thing. Guess forward active, solve the circuit with the guess, and then verify. In this case, the base current will be 12 minus 0.6 over 50K instead of 500K. The collector current, beta times the base current, is going to be 100 times this current, which comes out to be 22.8 milliamps. The output voltage is 12 minus IC, 22.8 milliamps times 4K, comes out to be minus 79.2 volts. Better watch out. You'll get shocked with this circuit. Oh, but we haven't verified the region yet. So let's verify the region. We have to show VBE is bigger than 0.4. No problem, VBE is 0.6. So we satisfy the VBE requirements. VBC has to be less than 0. VBC is 0.6 minus a minus 79.2. So VBC is plus 79.8. We violate that assumption. Okay, so we're not going to get shocked with the circuit, hopefully. We're not going to get 79 volts on the output. We don't have the right solution. So now what do I do? What? Guess again. Cut off or saturation. Let's guess saturation and see if it verifies. So if I guess saturation, what's the output voltage? It's what? 0.2. Does everybody see that? Does everybody see that? I love how quickly you got that answer. How did you get so quickly? You put in the model. The model in saturation was this, 0.6 and 0.2. And this was the collector. And this was V out. Okay, everybody see that? Okay. Now we have to verify this is valid. We have to show that, how do we verify this? Mr. Day.
With saturation, you want to make sure that that both the VB is greater than 0.4 and VBC is
greater than 0.4.
No, that wasn't our condition for, that would have been nice, but that would have been conditioned on the independent variables. In this case, we conditioned on dependent variables.
Do you check the currents?
Currents. We have to show that the collector current is less than beta times the base current. Let's check that out. Oh, it's more work to verify this than it is to solve it. The solution is pretty easy. To verify, we have to show that the collector current is less than beta times the base current. So now I've got to calculate the collector current and the base current. The collector current is equal to 12 minus 0.2, it's 11.8 over 4K. And the question, is that less than beta 100 times the base current, which is 12 minus 0.6 over 50K? Can you check that condition? Well, this current, do I have the current? I don't have the current written down here. Yeah, this current is the same as before. This is electric current beta and base current. So it's 0.228 milliamp. Whoops. This is 0.228 milliamps. And the question is that greater than what's this current here? Oh, times 100 times the base current. So it's 22.8 milliamps. And what's this current here?
2.95 milliamps.
2.95. So 2.95 milliamps is less than 22.8 milliamps, so we verify. So the output is 0.2 volts. Any questions so far? Play the same games we did for the MOS devices to analyze the circuit, right? Here's another circuit. I'm going to want to interpret IC and V out. I'm going to assume C is large and the V in is a very small sinusoidal voltage. It's so small, I'm going to assume it's a short circuit. How do I analyze this circuit? What's the current through the capacitor? What's the DC current through a capacitor? 0. So if this voltage is 0, there's no current through the capacitor, I can wipe this out. If I wipe this out, this is exactly the same problem we solved first. So the output voltage is what we determined earlier. So we've already solved this circuit. Are there any questions? Yes.
Activity is in the saturation range where I is still equal to I plus.
Yes, Kirchhoff's current law always applies. It always applies. Yes. Yes. Let me look at just a second. I'm gonna get this stuff.